Hello, my name is Adam Harnish. Today we're here to present to you some of the highlights of our research paper. And our research paper dealt with gas injection EOR, and we're also going to focus on unconventional side and the conventional side. So a little bit about the motivation behind unconventional gas injection EOR. Most shale reservoirs are on primary drive mechanisms. And so as we know, this is recovery is a highly energy intensive process due to the tight shale matrix permeability, which has poor fluid transport properties. And so as a result of this energy intensive process, our base recovery is approximately 8%. And so the ultimate motivation is 90% of our resource is left behind. Now I just want to kind of highlight three kind of big differences between conventional and unconventional gas injection EOR. First is fractures. As we discussed, in conventional, fractures aren't very good. It leads to channeling, which we don't achieve that piston motion, and that leads to early breakthrough. However, in unconventional, we need those fractures. We need a method to reach contact area with the reservoir, and so the existing fracture network is what we use. And so if we were to try to inject without it, it would take too long and be uneconomical. Minimum miscibility pressure, we'll discuss that in detail here in a minute, but in terms of conventional, recovery is maximized at this point, so we have to reach minimum miscibility pressure, which is basically the pressure at which the gas and oil become miscible. The difference in unconventional is as we go above that, we can exponentially increase our recovery, and we can 2-3 times recovery as we go above MMP. Conventional matrix, as we know, we only have an inorganic matrix component, but when we go to unconventional, we have a whole new inorganic matrix component that, as we'll see here in a minute, it's kind of one of the horizons that we need to understand a little bit better if we really want to understand the mechanisms behind unconventional EOR. As we discussed, minimum miscibility pressure, this is lowest pressure, which miscibility can be achieved. And basically, once we reach this pressure, the interfacial tension between the reservoir crude and the injected gas is 0, and therefore they're able to mix. And we can know this ahead of time because it's easily measured in a lab setting using the most popular slim tube method. And so we also have this kinetics vaporizing gas drive. And so this is the main drive mechanisms. And so understand that once we get to minimum miscibility pressure, it's not instantaneous. There's a mass transfer process that takes place. And so what happens is our gas is injected down to this point, and here's our reservoir crude. And this mass transfer takes place where this reservoir crude eventually, the lighter components vaporize into the crude and eventually gets lighter. And there also can be an enrichment process of the gas, which takes on the heavier components of the crude. And once we reach this critical point, then miscibility is reached. Containment. Containment is another important recovery mechanism, and we need to kind of think of the reservoir as a tank. However, we need to reconcile the fact that we use the existing fracture network to displace our gas with increased contact area. However, we need to pressure up the reservoir so we can get above our MMP. So there's kind of a trade-off. And there's been some field trials that have done. And for instance, in the Eagle Ford, gas injection has worked really well, and it's been a total failure so far in the Bakken. And kind of what they're alluding to is they think containment is this important determining factor of success or failure. 2 quick operating parameters that we find that works best for unconventional is CO2, and that's due to its a lower MMP, which means it's less compression, cost advantage. Reduces viscosity, makes the oil lighter, and it has a high diffusivity, so it doesn't take as long to diffuse into the crude. Huff and puff, that's a cyclic injection and waiting for production, and so also we need a soak time. Again, we need soak time to let the gas diffuse and let that mass transfer process take place that we just spoke about on the ternary diagram. Final thoughts for unconventional. we know it's feasible. We've tested it in lab setting. It does work. However, when we get to the field, we need to understand this containment. So we need to better understand the candidates that this will be applicable to. And so with that, we need to, as we mentioned, that fracture reconciliation with reaching the minimum miscibility pressure. Lastly, we don't really understand the flow mechanisms behind the inorganic component. There's been some theories out there that due to the meso and nano-sized pore particles or pore sizes that Darcy flow may not govern this process. And so until we understand the flow mechanisms behind this, we really kind of not really sure at this point. And again, the ultimate motivation, 90% of our resources left behind, and we already have the existing infrastructure in place. And so this oil will be incrementally extremely cheaper compared to the initial production.
First off, for CO2 injection, I like to talk about miscibility, and that's where it's usually fluids can just mix very easily. And if CO2 is injected above the minimum miscibility pressure, interfacial effectively disappears, which it lowers your viscosity as well as improves your mobility. Mixing the CO2 allows the CO2 to displace oil from the pore spaces, and that pushes towards the producing well. And if the reservoir pressure is above minimum miscible pressure, then theoretically recoveries could be as high as 90%. The taper WAG is like the conventional water alternating gas, but instead gradually reduces the injected CO2 volume relative to the water volume. This improves the efficiency as a flood, as well as prevents early breakthrough. All right, next page. This is the case study that I did research on. It's the Shell's Oil's Denver unit in the Lawson Field in West Texas. And this shows oil and water production as well as water and CO2 injection for more than 60 years. And as you can see, the primary production portion of this field's life ended in 1965 when the operator initiated pressure maintenance with a water injection. And you can see that tertiary recovery started in 1983 when they injected CO2. And you can see in the oil production curve, the slope in the secondary recovery seems to decline rapidly. And if you follow that slope, that would have been like if there was no CO2 injection. But with CO2 injection, it decreases the decline rate, how much the decline rate actually declines, and gives you a higher incremental recovery. And this is just proof that it does work and it is very effective. And this, in the past 15 years, it recovered a very good amount. Ready for the next page. And the last thing I want to talk about was carbon capture and storage. And carbon capture and storage is a process of capturing waste carbon dioxide from large point sources such as fossil power plants and storing them. And my thought as well, if we find technology to improve this, then we can improve carbon capture and storage, carbon capture. We can increase the supply of CO2, which would reduce the price of CO2, which makes CO2 injection more economically viable. And it's also, with the CCS technology, it also reduces emissions greatly. So on top of capturing more CO2, we'll also be injecting this into the well, and 40% of the CO2 is lost to the reservoir, but 60% of that comes back up and can be re-injected back into it. And so I'd rather have CO2 lost to the reservoir instead of into the atmosphere. So it's better environmentally and economically to focus on carbon capture a little more for CO2 injection.
I'm going to talk about natural gas injection, methane. So when the pressure in the reservoir is low, primary method of recovery, which rely on the natural gas viscosity of crude oil, cannot be applied to mine the oil. And if it is used, the output can be very low. In such situations, a secondary recovery method, which is in this case gas injection, has to be applied. Methane injection as a form of gas recovery method is one of the most effective methods which can be used to enhance the oil recovery. Methane and crude oil are partially soluble when mixed. Dissolving some methane gas in the crude oil helps to reduce the viscosity of the oil. which enables the oil to easily flow out of the well. The addition of methane gas increases the production of crude oil and by increasing the pressure in the oil formation. Reasons for using methane injection. Gas injection enhanced oil recovery methods has grown to become an important solution to natural gas disposal. This is an economical way which can be used to dispose of the uneconomical gas production which usually happens in the oil recovery process in the reservoir. In modern recovery methods, the method of burning the natural gases is no longer practiced as it has been declared illegal in some countries. Burning of hydrocarbon is not an environmentally friendly exercise. It results in the emission of high levels of carbon dioxide gas to the atmosphere, which plays a phenomenal role in global warming and climate change. Natural gas injection is an alternative way. The natural gas emitted during the recovery of injected is injected back into the recovery process. So it enhances the pressure maintenance. The produced wet methane gas from the oil fields is stripped of its natural gas liquids, compressed, and then pumped into a wetting injection well. For the study case, it is a non-miscible reservoir. The purpose of the project was to enhance the oil recovery of a mature carbonate reservoir. The introduction of gas injection successfully improved the output of the oil from the reservoir. The injection of natural gas leads to an increase in the GOR, and the total output of crude oil from the reservoir has been on the rise since there has been improvement in the mobility of oil due to the swelling effect caused by the injection of the gas into the system. And the main conclusion were that although the miscibility could not be achieved at current reservoir condition, a significant oil gain could be expected from a strong swelling effect of the reservoir oil. Around 70% of the oil volume increase at the reservoir conditions.
2 more minutes.
And now we'll talk about the viability of various gases used in EUR. Gas injection is very common in enhanced oil recovery process. Usually gases are classified into 4 types of the basis of injection, which are nitrogen and flue gas, and hydrocarbon, which is the natural gas, and the carbon dioxide, which is the CO2. Nitrogen and flue gas have a common strategy. These gases are cheapest, low recovery cost, and minimum miscible pressure, which causes the gas to be miscible in oil. Their viability is limited to deep reservoir due to the high miscible pressure. Nitrogen injection techniques was used in 1988 by horizontal well drilling. Through different literature and analysis, there are 2 active nitrogen injection projects in the United States. One of them is located in West Texas, which is the Yates field, and the other one is located in Florida and Alabama, which is the J. They use the WAG and the nitrogen. The economic evaluation table shows that the flue gases has the lowest cost of capture, compression, and transportation, followed by the nitrogen and the CO2, and the last goes for natural gas. It also shows the rate of injection, that the flue gases has the highest rate of injection, which is the 280,000. This plot shows the difference. This plot shows the gas-oil ratio with the time. It shows the GR of CO2 has the highest GR, and then followed by the flue gases, and then the nitrogen.
Now it comes to the hydrocarbon, also called natural gas. This is an alternative way of injection. The process of hydrocarbon has three methods, which are the compressed gas injection, and the liquid petroleum gas injection, and the lean gas injection. We normally use the lean gas injection because it has less cost effective. Due to the development of technologies with the compatibility of CO2 injection, we got CO2 as a byproduct. The process of CO2 EUR involves vaporization of the oil as the gas interacts with the oil reservoir. The whole process creates favorable condition for immobilizing. We can improve the viability of CO2 technology by increasing the CO2 gas stream injected. It will increase the sweep efficiency, improving well designs for better recovery, widening the range of fluid miscibility, enhancing the mobility ratio between injected fluid and residual oil. Thank you.